And
sì, introduco, mi sono dimenticato, ci parlerà di osservazioni, previsioni, impatto ambientale, i benefici del radar meteorologico Vaisala in doppia polarizzazione.
Closer to the microphone. Okay, thanks. So thank you very much. And as you can see, the title of my presentation is in Italian language, but I will speak in English, so thank you for accepting this English talk. My name is Pekka Rossi, and I'm an application manager for Vaisala weather radars. In this presentation, I will give a short introduction to weather radars in general. Okay, now it's better. So I will give a short introduction to weather radars in general, and then I will focus on a new technology called dual polarization technology. As you know, Vaisala is a company that manufactures different kind of weather instruments. We have a long history of manufacturing and delivering, for example, sounding systems and surface weather systems, but we also deliver dual polarization weather radar systems. And dual polarization is a technology that is becoming more and more important in the operational weather radar meteorology. So today we saw some nice examples of the satellite-based radar systems. In this presentation I will only focus on ground-based weather radar systems. And for those who are not that familiar with weather radars, I will give here a short introduction. So what is a weather radar? Weather radar is basically an instrument that is applied to identify different kind of precipitation-related weather phenomena. And as the name implies, the weather radar is a radar, so the basic principles of a weather radar are very similar to those of any type of radar. For example, the radars that are being used in the aviation applications. So it's an active remote sensing instrument that sends pulses, electromagnetic pulses in the atmosphere, and when these pulses, when they meet some targets in the atmosphere, for example, precipitation particles, part of the energy of the pulse is reflected back to the radar, and the radar has a very sensitive receiver that can detect these so-called radar echoes. And this information can be interpreted as information on the precipitation. And modern weather radars, they have many advantages over conventional weather instruments such as rain gauges. And one of the biggest benefits of modern weather radar is that they can efficiently monitor and cover phenomena with different scales. With weather radar we can get accurate information on small and local thunderstorms, and we can simultaneously get information on larger weather systems such as large frontal systems. High resolution and large coverage is also a big advantage of weather radar, for example, when compared to the rain gauges. Individual weather radar can cover the area that surrounds up to 250 kilometers in range, or even more in some cases, with the resolution that varies from a few hundreds of meters to a few kilometers. So at each point in this area we can get precise information about the precipitation and related phenomena. Fast measurement cycle is also an important advantage. We can get updated information about the weather situation with the interval of the few minutes, and this is very important when it comes to the monitoring of fastly evolving phenomena such as thunderstorms, which are causing a lot of damage at the ground level. And weather radar enables not only detection of rain or precipitation, but especially modern technology such as dual polarization enables detection of other phenomena that are related to precipitation or that are inside the storm, such as shear, or we can identify different hydrometeor types such as hail, crawple, and so on. So as we have learned today, precipitation is pretty much a global phenomenon, and we can basically have precipitation almost everywhere in the world. Of course, we might have some areas where the precipitation is not so common than in the other places, but it doesn't mean that the information about the precipitation would not be important. It's actually extremely important. And therefore, it comes as no surprise that weather radars exist basically everywhere in the world. So we can have weather radars in the tropical conditions close to the equator, or we can have weather radars in a harsh Arctic conditions. And Vaisala also has delivered weather radars almost on all continents. And these weather radars, they bring lots of added value to different end users. So there are many applications that can be built upon the information that we get from weather radars. And here I have a list of a few applications that are important to different end user groups. With weather radars, we can do accurate nowcasting and short-range forecasting. So if we take a sequence of weather radar images, we can actually extrapolate the movement of storms and do very accurate nowcasting of individual thunderstorms. We can also do accurate quantitative precipitation estimation, and the advantage of weather radar in this regard is, for example, that weather radars, as opposed to individual gauges, they can cover large areas, and being able to cover the entire catchment areas is extremely important in hydrological applications. Weather radars can also not only detect the locations of individual storms, they can actually detect the vertical structure of the storm. So weather radars actually measure the three-dimensional structure of the atmosphere, and this is very important when it comes to the warnings and analysis of the severe weather. Okay, so what does a weather radar actually measure? So here we have the three main measurement types of a conventional weather radar. So the first and most important measurement type, or the parameter that we get from the conventional weather radars, is the so-called radar reflectivity factor. And it's related to the signal power that we receive at the radar site or at the radar receiver. And in general, the more intense is the signal, also the more intense is the radar reflectivity factor. And in general, the more intense is the radar reflectivity factor, also the more intense is the precipitation that we are observing with the weather radar. Another parameter is the radial velocity, and this has been existing since the existence of Doppler weather radar systems. So Doppler weather radar systems can detect the velocities within the measurement volume of the radar. And this means that it's not the true velocity, but the velocity that is moving towards the radar, but it's related to the winds inside the precipitation. And with this parameter, we can also derive lots of wind-related products, such as wind fields, or identify shear. Then we have the third parameter, that is the spectrum width, that describes the variation of the radial velocities within the measurement volume, and it can be, for example, to indicate turbulence inside the measurement volume. So what is then a dual polarization radar? How does it differ from a traditional weather radar? So in traditional weather radar, we send only one type of pulse in the atmosphere. And this pulse has the electromagnetic plane that is polarized in the horizontal direction, so it's a horizontally polarized wave. In dual polarization weather radar systems, we actually send two types of pulses: the conventional horizontally polarized wave, and then additionally we send vertically polarized wave. And these two independent samples, they behave a little bit differently when we have different precipitation types in the sample volume, and it provides information on the type of the scatterers inside the measurement volume. Based on these two independent samples, we can also derive a number of new parameters that can be useful in different weather radar applications. So for example, we can estimate the so-called differential reflectivity, that is the ratio or the relative difference between the received powers from the vertical channel and the horizontal channel. We can also calculate the correlation between the two independent samples, and this gives information about how homogeneous the precipitation particles are inside the volume. We can also calculate the phase difference between these two samples, which gives information, for example, about the water content inside the measurement volume. Or then we can calculate the so-called specific differential phase, which is just a range derivative of this differential phase, and that can be used, for example, in accurate rainfall estimation. So as you can see, we have quite a number of new parameters when compared to the traditional weather radar measurements. So what is the benefit of having these measurements? What do we gain by these? So the benefit is that we can actually improve the quality of the weather radar observations and build new applications and products that bring lots of added value to the end users. And here I have 4 main benefits that the dual polarization radars provide. Of course, the list could be longer, or the order of these benefits could be changed, but this is the list of benefits that we consider as the most important. So first of all, the dual polarization measurements, they help to detect rain patterns and remove the clutter from rain patterns more efficiently. So with dual polarization radars, we can actually identify different clutter targets and disturbances much more efficiently than with the conventional weather radars. We can also extend the detection range by enhancing the sensitivity of the radar. So we can actually, by enhanced sensitivity, we mean that we can actually detect weaker weather radar echoes. We can also improve the quantitative precipitation estimation, and we can also classify the different hydrometeor types. In addition to those, there are some environmental benefits that come, for example, to the use of the power at the radars. So modern dual polarization radars, they can actually reduce the power consumption by having less transmitter power. So here I have an example that illustrates the different phenomena in the atmosphere that the radar actually is exposed to. So, of course, we have in the atmosphere the weather targets, for example, the rain clouds that we would like to measure with the radar. But then we have also many other types of targets in the atmosphere, such as insects, and we have birds, aircraft, chaff, which may cause some interference or disturbance in the weather radar measurements. And if we're not able to filter out these echoes from insects, for example, we may misinterpret these echoes as weather echoes. So therefore, it's important to get rid of those clutter and disturbance sources. We may also have echoes from the ground, especially close to the radar, or we may have also interferences from the other electromagnetic sources, such as wireless LANs, and which are becoming more and more problematic in the operational weather radar world. I would like to illustrate this radar's capability to remove these non-meteorological echoes by this historical example. Here we have an example how the weather radar images looked like before the invention of digital signal processors and digital computers. So basically, we only had the analog display where we could see this very simple monochromatic blob showing the weather pattern. And it was quite difficult to interpret this information. Later on, when the radars developed and the digital signal processors and digital computers were introduced, we were actually able to color the images to show the intensity of the echoes. And now we can see that, especially close to the radar, we have some high intensity pixels here. And these pixels, they come from the nearby ground targets. So they are not real weather echoes, but they are false echoes that actually disturb the interpretation of the weather radar images. After the Doppler technology was introduced, it was invented that actually we could use this Doppler information, the velocity information, to remove these ground targets from the weather radar images. And the key idea behind this is that actually the ground targets, they are not moving, but the weather targets are moving. So perhaps we could use the velocity information to filter out the ground targets that are disturbing the weather radar images, especially near the radar. And by these kind of filtering techniques, we were able to, or the weather radar community was able to filter out most of the ground clutter targets from the radar images. You can see that the image is significantly improved. However, there are still some remaining residual clutter targets nearby the radar. Additionally, there is some very spurious echo here, which is also not a weather target. And actually, this radar image is measured in Helsinki, close to the sea line, and this echo is actually on the sea. So this is sea clutter, and sea clutter is also a problem in some atmospheric conditions. And sea clutter comes from the ripples and waves of the sea, so it's immune to Doppler filtering because the waves are also moving, so it cannot be removed by Doppler filtering. But then, if we have a look at certain polarimetric parameters, we can see that actually these non-meteorological echoes, such as waves, they actually stick out quite well in this polarimetric image. So we can see here we have a correlation coefficient, and we can see that the weather patterns here, they are quite well pronounced when we compare to the sea clutter. And by cleverly combining different dual polarization parameters, we can actually filter out very efficiently the residual clutter targets from the image. So the key to this high-quality data is to have the first digital signal processing and then apply Doppler velocity measurement filtering, and after that apply dual polarimetric information to remove the residual clutters, to have the information that is relevant to the end users. And this kind of filtering also can be used against wind turbines, at least to a certain extent, and the disturbances from external emitters such as wireless LANs. And as I explained, both of these are actually becoming more and more problematic in the operational weather radar world. We have more wind turbines, and also we have seen recently some increase in the disturbances in wireless LAN interferences. Okay, so the second benefit that I would like to talk about is the extended detection range by enhancing the sensitivity of the radar. And in conventional weather radars or the traditional single polarization radars, the detection of the radar reflectivity is based on the measured noise at the based on the measured signal power at the receiver. But the signal actually consists of noise that come from various sources and then the true signal of the weather target. And this noise is very problematic from the viewpoint of the detection of weak echoes, because if the noise is too large, it becomes very difficult to detect the weak weather radar echoes. But in dual polarization radars, we actually have these two independent samples sent in horizontal and vertical direction. And it's well known that the weather signal retrieved from these horizontal and vertical pulses, the weather signal is very much correlated, while the noises in these two signals are uncorrelated. So this means that by using some clever cross-correlation techniques, one can actually improve the sensitivity of the radar measurements. And at Vaisala we have developed this enhanced radar reflectivity detection that is built upon this cross-correlation technique. And here I have some example of the conventional weather radar reflectivity. And if we apply this kind of cross-correlation based enhanced sensitivity, we can actually see that we can detect weaker echoes that are here in the surrounding areas of the radar reflectivity pattern. So this way we can actually extend the detection range of the weather radar. This also has a relation to life cycle and environmental sustainability, because one way to improve the sensitivity of the radar is, of course, to have a high power transmitter, to increase the transmitter power in the radar. But of course, having a higher transmitter power increases also the energy cost and the life cycle costs of the radar. So by using this kind of correlation-based enhanced sensitivity, we can actually keep the transmitter power on a lower level and this way save some energy in the radar. Another benefit is the improved quantitative precipitation estimation for the purpose of hydrology and emergency response. And this is, of course, an important application, or one of the most important applications of weather radar. So with weather radar, we want to not only detect where the rain patterns are moving, but to estimate the rainfall intensities in a quantitative manner. And one of the reasons why conventional weather radars sometimes fail in quantitative precipitation estimation is the signal attenuation. If we have, for example, high intensity precipitation, the signal that is transmitted from the radar may attenuate so much that it results in significant underestimation of the rainfall. However, in dual polarization, we actually have other parameters that can be used to correct for the attenuation. For example, we can use the specific differential phase, or the phase difference between the two pulses. And because the phase difference it's a phase measurement, it's insensitive to attenuation. However, the phase difference is sensitive to water mass inside the radar sampling volume. And we can see here in this example that this differential phase, it shows quite nicely the areas where we have signal attenuation. And we can use this as an independent reference when to correct for the attenuation. So here we have an example of intense weather pattern in Helsinki, measured by a weather radar in Kumpula, Helsinki, and we can see that there are certain parts here that are clearly attenuated. However, if we add the dual polarization information, you can see that some of the areas, or most of the areas that were attenuated, actually can be corrected with this dual polarization based technology. The dual polarization radar can not only correct for the attenuation, it can actually improve the quantitative precipitation estimation in terms of the absolute rainfall amount. So it's scientifically shown quite well that these differential, specific differential phase-based methods, they work better in heavy rainfall than conventional radar reflectivity-based rainfall measurement techniques. And the advantage of these techniques is also that the KDP is insensitive to signal attenuation or the calibration errors, so it can be used also in the case of attenuation to estimate the quantitative amounts of precipitation. The last, but definitely not the least important application on my list is the classification of different precipitation types. And as I already mentioned, with weather radar, with dual polarization weather radar, we can actually get many new parameters that describe the properties of the precipitation particles inside the radar measurement volume. And by combining these different parameters, we can actually classify the type of the precipitation. So here we have an example which resembles very much a conventional weather radar image. We have colors, we have the areas where we have identified the rainfall or the precipitation, but in addition to the locations of the weather patterns, we can actually see here indicated with these different colors the type of the precipitation. So we can see, for example, that here we have liquid precipitation rainfall indicated with the green color, and in this particular case we had some convective activity where some hailfall was identified, which was verified by this photograph. And as you can imagine, that having this kind of information in addition to conventional weather radar measurements such as radar reflectivity factor, this kind of information can bring lots of added value to several end users such as aviation. I've been talking quite a lot about these different parameters and dual polarization based parameters and products, but it's important to note that it's not possible to have high quality products and parameters without hardware that is optimized for dual polarization measurements. And in addition to signal processing and algorithm development, one of the key competencies of Vaisala is that we actually put a lot of effort in the hardware that is optimized for dual polarization information measurement. And for example, antenna of the dual polarization radar is one of the most important hardware pieces, and it's important to have, for example, the low side lobe level, which guarantees that the electromagnetic waves that are transmitted by the radar are accurately focused. It's also important to have carefully matched horizontal and vertical beams that ensures that we actually measure the same volume with the both polarization planes. And it's also important to have good cross-correlation polarization isolation that ensures that the signals from the two independent samples are not mixed. And actually, all Vaisala antennas delivered in different weather radars, they are measured, and the antenna measurement report is provided to the customer. So to conclude my presentation, I have here three main things that you should remember about the dual polarization radars. And the first thing, when we compare to the traditional weather radars, is that dual polarization radar can actually see much more than conventional weather radars. So we can identify different precipitation particles, we can achieve higher sensitivity, and this way extend the detection range of the weather radar, and we can also improve the quantitative precipitation estimation of the radar. We can also achieve a better quality of the data, which is very important because otherwise we may interpret the echoes in a false way. So for example, if we have disturbances from the sea, if we have disturbances from the insects or wireless lands, they are problematic, especially for those end users who are not radar experts. And to ensure the good quality data, we must be also, to ensure the good quality data, the radar must have also the hardware that is optimized for dual polarization. And I gave you an example of the radar antenna that is one of the most important pieces of a weather radar. And without a good antenna, the first 2 points here could not be fulfilled. So that was all I had. Thank you for your attention.
Thank you, Pekka, for your amazing presentation, for a complete presentation. But I have any question.
Yes.
It's Amazon product, but how much cost this product? Because the product is fantastic. But,
well,
and also, where is the maintenance interval?
For a weather radar?
Yes.
Well, we have
this specific weather radar.
We recommend that we have different maintenance schemes.
Yeah.
So we recommend that the radar site is visited, for example, every half a year.
Yeah.
And there are also, for example, automated calibration methods that then keep the calibration level of the weather radar automatically on a good level. And as for the price, it's always depends. It depends very much on the project. That's something that I cannot say, because the radar project is always composed not only about the radar itself, but there are also extensive civil works. For example, the radar tower, you have to provide electricity to the radar site and then build a road.
All inclusive. The cost all inclusive for an application of civil protection?
Yeah, well, it's a difficult to estimate, but in general, weather radars are, the price range for weather radars it's I mean, it's a million class instruments in euros. Anyways.
Thank you. Any question for the public? Also. Please, Professor.
Since I've been playing a lot in the past with dual polarization and also precipitation classification, right? So using KDP, FIDP, and all these very interesting, quantities. I would like to ask you, how do you calibrate your precipitation classification? How do you
verify it, or
well, okay, let's put it that way. How do you verify? How can you say that there is hail and somewhere else there are graupels and things like that? Do you do with?
Well, it's of course a good question, calibration or verification of hydrometeor classification, because the radar, it measures the precipitation particles aloft. Of course,
right.
You can use ground verifications, but the ground verification does not always match with what is observed aloft. So what we have relied on, we relied on the best practices that have been presented in the literature.
Okay.
Please, Professor.
I have also a very quick question. During your presentation, you mentioned that with this new generation weather radar, you can obtain better estimates of precipitation, the amount of precipitation. Can you provide some numbers? And these numbers depend on the type of precipitation, type of event that we consider, or are they independent?
Yes,
and how do you evaluate the accuracy?
Well, there are a number of scientific studies that actually show that these.
But roughly, just.
I don't remember by heart any numbers,
okay.
but I can provide those to you. But to add to that, these precipitation estimation methods work for liquid precipitation.
Yeah. Okay. Thank you.
Thank you. Any question? Another question? No. Ok. Thank you, Pekka. Thank you.
Thank
now.
you.
E allora io chiamerei qui, abbiamo terminato la sessione, chiamerei qui il professor Zardi per per eventuali comunicazioni. Io vi ringrazio per la vostra attenzione, per aver pazientato fino a quest'ora, perché comunque la giornata è stata lunga, e quindi cedo la parola a Dino per comunicazioni relative a questa serata e per il proseguo dei lavori di domani. Grazie ancora.
Grazie Massimiliano per aver condotto molto bene e con ottima tempistica la sessione. Due note proprio di servizio. Abbiamo concluso parlando di radar, domattina riprenderemo riparlando di radar, in particolare della rete radar nazionale. Il primo relatore alle 9 sarà Frank Marzano. Si conclude qui la parte ufficiale del festival di oggi, però vi faccio presente che alle 18:30, sempre in questa sede, ci sono due eventi, chiamiamoli così, collaterali. Nell'aula meeting c'è una riunione informale delle associazioni amatoriali. Si è parlato oggi di associazionismo, le associazioni sono presenti al festival e hanno deciso di presentarsi tra loro e presentarsi agli altri. C'è in concomitanza però un'altra assemblea di associazione qui in questa sala alle 18:30. L'Associazione Italiana di Scienze dell'Atmosfera e Meteorologia tiene un'assemblea ordinaria per definire un adempimento formale, che è la nomina dei revisori dei conti, e anche per rincontrare i soci che si sono visti recentemente a Bologna per l'elezione degli organi sociali, ma un aggiornamento non fa mai male. Quindi il direttivo ha ritenuto che, sfruttando il fatto che molti sono comunque presenti per il festival, poteva essere il caso di rivedersi. Quindi, ripeto, alle 18:30 questi due eventi sono in concomitanza ma non sono in conflitto perché si rivolgono a soggetti diversi. Qui ci sarà l'assemblea dell'Associazione Italiana di Scienze dell'Atmosfera e Meteorologia. L'assemblea di per sé è rivolta ai soci, ma se i soci non hanno nulla in contrario, io penso che la possiamo anche tenere assolutamente aperta perché non abbiamo segreti. Invece alle 18:30 sempre nell'aula meeting le associazioni amatoriali. Ricordo che questa sera alle 20:45 al Teatro Zandonai in Corso Bettini si tiene il concerto di Cecilia Scelli, però vi ricordo che si sarebbe dovuto prenotare come segnalato sul sito e tutto quanto. Non escludo che qualche posto sia ancora disponibile, ecco, però tenete presente che nel caso bisogna essere là con un certo anticipo rispetto all'orario di inizio, che è, ripeto, le 20:45. Grazie ancora ai relatori di oggi, ai quali farei ancora un applauso, e a più tardi.